In this demo, I want to show how to design a tiny Hello World cancer drug. New molecule that looks like the old molecule, has the same properties, but has more asparaginase characteristics. I'll give you the ChatGPT crash course about ALL, leukemia, asparaginase, and asparagine, these 4 keywords. So for people who come from software and AI background, so asparagine is an important amino acid needed by leukemia cells to grow. Fact number 1. 2, asparaginase is an enzyme that breaks down asparagine. And 3, in ALL, which is special version of leukemia, the leukemia cells need asparagine to multiply. By using asparaginase, doctors can reduce the amount of asparagine available. So we starve the cancerous cells from the material that they need most. This helps to inhibit the growth of leukemia cells in ALL patients, right? So if we can design a more effective asparaginase molecule, that would be pretty cool, right? So that's what we are trying to do in this demo. So I'll start by loading asparagine smiles here. So it connects to our database, our search API, and it finds the smile. This is pretty small molecule. It's just 1 amino acid. And then I start with the existing asparaginase that Kathy found for us in this particular species. I go its size less than 400. We want to work with smaller proteins for the demo, because the larger the protein gets, usually the model's computational complexity grow quadratically, so we don't want to waste your time. So we go with the smaller molecules for the demo. So I pick one of them, this one. These are very random processes, so we might get different results with different runs. So hopefully we get some cool results today. We can get one molecule that has better docking properties or other properties in terms of being asparaginase. So we start with folding this. It finds the ESM fold, that a model that was developed at Facebook, AI research, and 5 seconds on an A10 GPU, and you get a very nice looking, it's a 2-piece protein, has a head and a tail. So, and now I dock the asparagine on top of this protein. Again, very simple chat. It finds the right model, it connects to the right model, it runs it on GPU. We serve all these models at the moment ourselves. And now you're going to get some docking graphic and also a score here, -0.73, which is not bad, but not very good. It's a very average score in this context. Like, that's the score of, think of it as a binding affinity score somewhat, and you can see the small molecule. Now what I'm going to do is I say diversify P1 with temperature. I take 1.6 and add asparaginase. So what this means is basically I ask the model to double down on that property and feature. So the model understands what being asparaginase means. It tries to add other features that are relevant to that and make a new molecule that looks like the old molecule, has the same properties, but has more asparaginase characteristics, right? And now I dock S1 on P2. So again, this is a very random process. We get different results. We're hoping to get a nice docking here. Again, it connects to the DiffDock, which is the MIT model that came out 2023. It runs it with a NUM cycle of 10, and you get to -0.47, which is a better score, right? So again, in 2-3 minutes, we design a new protein that has a better docking score. These are random. At this particular example, we succeeded. Most of the time we succeed. There are also some failures. That's what we did. We basically designed a new protein that has the same characteristic as the old one. If you want to check the sanity score guardrails, we make sure we're not hallucinating. I compare P1 and P2, and again, it finds the right model, which would be ProtNLM, the model that came out of Google research, and do a comparison of the features, the TM scores. You can see everything here. Actually, in terms of being asparaginous, according to ProtNLM, the new protein has a higher score. This is another good thing. We call it the improvement. But again, you obviously have to take this to the lab. And in terms of being L asparaginous, which is more about active asparaginous, we even improve higher, right? So these are all good results, and we hit a better docking score. So we can say this could be just a tiny candidate for you to do your own research for developing ALL treatment, right? We don't claim here that you can cure ALL. We don't expect you to produce this molecule and feed it to somebody with cancer and just cure the person. That's not what's going to happen, but you get the idea, right? We develop something cool in a few minutes. We are going to improve our core end-to-end generative AI model, so that we're hoping to improve all these numbers and metrics a lot.